So, hello guys. Welcome to the comic relief talk of this conference. I will talk a little bit about how machine learning can actually be mixed with art and how we can create stuff from existing artwork or existing images, and we can create something new by mixing and matching that. But first of all, I'm going to start by talking a little bit about a show that I really loved when I was a child. It's called Art Attack. I'm pretty sure none of you know it because apparently it's not a thing in Russia. There was this guy like in the 90s, if you were a kid in the 90s and you were a kid in Brazil, he would just teach kids how to make stuff from like cardboards or other like trivial materials out there. Apparently it's sort of similar to this Russian show. Good response. Yeah, you know it. So yeah, it's pretty much like this. Which name I cannot pronounce. And the guy used to like get a bunch of clothes and like put it on the lawn, and he would just get these funky images. Also, he would get a bunch of flour or salt or sugar, and he would just lay down on the floor, and he would get these amazing visuals. And of course, when I tried to reproduce that as a kid, because I was very artistic, as you can see, I would get something like this. Except it was just one child, because I'm a single child. And nowadays, I express myself artistically by dancing. I really like dancing. And actually, I was dancing in the opening and closing ceremonies of the Rio 2016 Olympics, which is pretty cool. I'm one of those green things, and which led me to appear in international television for 5 seconds. So like maybe you saw me on TV, which is pretty exciting. I have no idea which athlete is that, but I remember she was French. And I also express myself artistically through code, which is pretty cool because most people don't know, but code is also can be like a very good artistic manifestation. You can really express yourself artistically through code as well. And therefore, I can teach the computer how to make art. But yeah, what do you mean, Isa? Make the computer make art? I will get there. So hi, I'm Isa. This is my Twitter handle. This is my baby, as in Russia. And I'm a developer at Work & Co. I do like front end, back end, whatever it is. And I also love maths. I do slalom inline skating. And I have a peculiar sense of humor. And let's start by talking about art. So what is art? I know that it's a very like difficult concept, it's very shady, and it's obviously vague because art can be anything you want. So I got this 4 definitions. The first one is like the most down to earth. I got it from the dictionary. And according to that, it's a quality, production, expression of whatever it is that it's appealing to other human beings. Which makes sense. It's usually how we think about art in the first place. But Paul Gauguin said that art is either plagiarism or revolution, which I completely agree. Art can also be harmony, according to Georges Seurat. And my favorite definition is by Leo Tolstoy, and he says that basically it's anything that you're able to create that inflicts emotions on other people when they see the things that you did. That for me, I really agree that that can be considered art. But okay, like a couple of questions now. Does it have to be beautiful or original? Because like when we think about art, and what I hear a lot of people say is that like, okay, I just went to this museum and there's this random images. I could have done that. How is that art? How is the square in the wall art? So does it have to be complex or have monetary value? Does it have to be like auctioned by millions in auction fairs? Does it necessarily have to be the case? Or does it even have to be made by an artist? Like, what if I just have the idea and someone else creates it? So a very good example of that thing is a work of art that I really like. It's called 1 and 3 Chairs by Joseph Kosuth. I got to see it, I got the chance to see it when I was in New York for the last time. It was in MoMA. So what happened is that like you get to the museum, and there's 3 manifestations of a chair. There's the actual chair, there's the picture of a chair, and there's the definition of a chair. But the thing is that he didn't do any of these 3. He didn't like make the chair, he didn't take the photo, he didn't write the definition. So why was that even a mama? Where's the art here? We'll also see that in a sec. So okay, going to the machine learning part, which is probably why most of you are here, since I got this briefing from the organization that Russian people really like technical details. So I got a lot of hardcore stuff to show you. So what is machine learning? Because I also hear a lot of people talking about machine learning this, machine learning that. Let's just predict the results using machine learning. But what is it? Because I don't see many people defining it, just see people using the terms and stuff. So machine learning is an application of artificial, and I mean, fuck that. It's just like something that allows a machine to actually learn. And that is a very good definition because the way the machine learns in this case is going to be very close to how we as humans learn. For example, you don't born knowing what a dog is. Eventually you see that many dogs and you just start like getting these approaches in your head that you know that if you see a furry thing and 4 legs and barks, you know that it's a dog. So like you learn by example. It's one of the ways that you can learn, you can teach machines how to do stuff in machine learning. There's others. But the important thing here is that we no longer have to create like a very different set of rules. Like we don't have to create a giant switch case statement to teach a computer what to do in every single occasion. The machine can infer that by using the examples that you're feeding to it and whatever it is that you expect the machine to give it back to you. And another very good way to define that would be like, it just allows us to feed very large chunks of data. So by the way, you can just get a lot of events and stuff from users from Amazon, for example. Like Amazon has a really, really very big use base. And like, we're not gonna necessarily analyze one of those users and see whatever they like. Those predictions and things that you can infer that the user is probably looking for buying, we can do that automatically because there's a couple of ways to do it, but we can just infer that, well, if we have a user that's like this and he has similar behavior to these other users, then maybe them both share some interests, so therefore I can recommend stuff to this other guy as well. So it's very automatic, and that's the cool part about it, because like if we were stuck into writing very specific rules for each of those guys, we would not like have life anymore. And the important thing here is just stating that there's a lot of very different problems, and each of those problems are going to have like appropriate flavors of JavaScript, of machine learning algorithms. For example, if you have a prediction problem, so if you want to know like, oh yeah, what is the average temperature in Moscow in December? So that's something that you're trying to predict. And for a prediction, you have like a couple of appropriate algorithms, such as linear regression. And if you have another problem like classification, like I want to know if an email is spam or not spam, you have a couple of other types, such as decision trees or maybe linear classifiers. So our mission today is working with images and to generate new artwork from existing ones. And to do so, we're going to need all these things. The first of all we're going to need is a very powerful algorithm, because in this case, since it's a problem related to images, we're going to use this kind of algorithm which is called deep convolutional generative adversarial networks. What? Yeah, like it's very difficult to understand it. The name itself is very confusing, but what exactly is this thing? Baby steps. It's just an algorithm that is capable to create new artwork from existing ones. The whole category of machine learning to do image-related problems, we usually call them like convolutional neural networks, CNNs. That's the algorithm that deals with images better because it gets images and like is able to dissect the matrix of colors and stuff. And this one, as you can see from the name, it generates new artwork from these ones that you're feeding it. and which is pretty cool. This algorithm is very new, I must say. Like the paper that proposed that algorithm was just out in by mid 2017, which in terms of like technology and especially machine learning, which is a very like research-oriented field, is it's very recent. So I think it's very interesting for us to like deep dive into like new stuff. So basically the way it works is that you have two convolutional neural networks, which is the single algorithms for images stuff, and we just put them to fight. And what do I mean by that? Basically, let's take its baby steps. So each algorithm works based on a model. You can think of a model as some sort of mathematical formula to do stuff, such as if you wanted to know the acceleration of a car, you would probably use Torricelli. At least that's what we use in Brazil. Maybe you have some more advanced formulas for that. But like you have a very specific way of solving problems based on whatever the problem is. So each algorithm works based on this model, and the types of model that we're going to use today, one of the neural networks is going to be following the discriminative model, which is just like an algorithm capable of like categorizing stuff. And for example, if you feed an image of a lake and you want to know if there's a duck in the image, that's probably the algorithm, the type of model that you're going to use. It's going to discriminate to you. It's going to tell you if there's a duck in the image or not. And the other one is the generative model. It's the one that's able to create new stuff. And you can have these type of models for different kind of problems. Like, for example, you can have generative models for sound stuff. You can generate new sound using machine learning as well. But yeah, in this case, since we're handling images, we're going to use a generative model to generate new artwork. And we'll use both of them, and that's exactly what's interesting about this, because since both of them have a very distinctive job, the fact that they're going to try to fool each other into being right and not the other one, that's what's going to improve the quality of the results. So I have a very specific scenario which might or not be legalized in Russia, but imagine if we're trying to generate images of IDs, for example. So the first neural net is going to be the discriminator. You can think of it as like the bouncer in the nightclub. His job is just to like take images of IDs and checking if that's an actual image, if that's real. And the other one is going to be like the teenager, 16 years old, that was using Photoshop. And his job is going to be to create images of as reliant IDs as possible. And we're going to put them to fight, literally. And at the beginning, it's very interesting because they suck. Because like none of them know exactly how to do stuff. The bouncer neural net is very bad at recognizing images of IDs because he's never seen it. And the other neural network is also very bad at creating them because he's never got to create them. So what happens here probably is something like this. Like you get this very lousy, low quality version of an ID. You feed it to discriminator network, and he's going to say, yeah, it's definitely true. Of course, why not? And at this point, we step into the execution of the algorithm, and we say, like, this is an image of an ID in Brazil, if you want to try to fake that. The thing is, and then we step in and feed the real image again and say, hey man, look at all these details that you're missing. Like there has to be a signature, there has to be a fingerprint. And the algorithm is going to run again, and this time he knows that it's not true. This time it knows better. So what's going to happen right now is that we're going to feed that false result. By the way, the answer is obviously not going to be false, super fake. What you get after this is like a scalar. It's like a number close to, it's going to be close to 0 if like the image is fake or there's some funky thing going on. So the values are going to be closer to 0 if it's fake, and if it's true, or if it's an actual image, or if it's very close to an actual image, the values are going to be super close to 1. And on the round 2, we're going to give that response. You can think of it as like 500 numbers to be simpler. It's actually like a vector of randomly generated hash numbers, which is what the neural net is going to interpret as like pixels, color pixels, to create the image. And we're going to feed that response into like, hey man, that one didn't work, and here are some randomly generated numbers. And the reverse deep convolutional neural network is going to use that and create a slightly better version of an ID. And well, the way that it works, and I'm only adding this because apparently you really like technical details, it's going to follow the minimax game. Some of you may know this from university, some of you may not, and don't worry, this is completely not fully necessary to understand the algorithm or the way that it works. But this is something that we call stochastic gradient in machine learning. Stochastic gradient is like the success rate of your algorithm. And what happens here, and that's on the paper that model was proposed, the first neural network, which is a discriminator, for as long as you want, or I mean, for as many steps as you want. This is the pseudocode for how it works. It's going to generate this noise samples. Noise samples are pretty much like the error rate. The error rate is very important in machine learning as well because it's what tells you how far off of the real answer you're really getting. And afterwards, it's going to generate the number of examples according to like, yeah, this is what I understand by an ID. And it's going to generate all these examples. And by then, it's going to increase a little bit what we call the stochastic gradient, which is like the success rate. The goal of the discriminator is getting that number as high as possible, because then it means that it's probably closer to 1, or in other words, that it's better at describing what's happening in the image. And after that part is done, we then go up to the generator, and the generator is going to generate all the noise samples, which is the error rate again. But this time, it's going to decrease the stochastic gradient, because the goal from the second neural net is trying to get the first one to fail. And successively. Like the goal of the first one is trying to get the second one to fail, and so on and so forth. So the second one is going to try to decrease that a little bit, which will increase their stochastic gradient. But what's important here to understand is just like the concepts. You don't need to remember all of this. You don't even need to know how to code this because, well, nowadays we have a lot of frameworks and stuff in machine learning that just like does stuff for us. It's pretty much like client-side development in 2008, like we use React, we use Angular. We don't have to code the render function of React every time we want to render stuff that's already made. And it's the same in machine learning. Like there's already a bunch of libraries and a bunch of frameworks with those things already coded, but I thought maybe you could be into the details. And the stochastic gradient, you may hear that in the machine learning quite a few times. It's nothing like, it's not a big deal. It's just a success rate into our problem. It's like how close we're actually getting to a satisfying solution. And this happens over and over and over again. The thing about machine learning, and especially about like image algorithms in machine learning, it takes quite a while. Like it can take up to days or like 16 hours or whatever. So we just leave the algorithm running, and just after a couple of days or a couple of hours, the algorithm is capable of generating all these images. As you can see, maybe it's a little bit blurry for you, but all of these are like images of bedrooms, but none of them actually exist. This image was in the original paper where Alec Radford suggested, first presented this approach to generating images. And the results for me are pretty like haunting, because if I saw any of these things in Airbnb, I would probably book that shit. And the fact that it doesn't necessarily need to exist is concerning. But it's also very interesting because you can also generate faces of humans. None of these people exist. They were made by this algorithm based on like previously fed faces of other humans. So it was able to generate those people. And getting to an even more scary level, you can have this. These people also do not exist. They were generated by this algorithm. And the thing about this is that NVIDIA ran this algorithm for like days. And obviously, NVIDIA has a lot of processing power, which makes this a lot easier. And these people were made by feeding a lot of images of celebrities. So as you can see, celebrities tend to be good looking. But yeah, none of these exist. And you're able to get a very accurate degree of detail if you're able to get this running for quite a while, and if you're able to adjust all the weights in the layers correctly, you can get pretty impressive results. And the way that I did my attempt of tackling this problem, I heavily based myself into this implementation, so feel free to check it out. It's going to be cool. Don't worry, I'll upload the slides. You don't need to desperately take pictures of this. But yeah, the second thing here is just getting a couple of thousands of paintings, because it's probably, it's what's going to be the fuel for our algorithm. And I went to WikiArt, which is this Wikipedia of art stuff. And my first idea was, well, I'm just going to get everything that Picasso has ever made, and I'm going to see if that's any close to whatever we expect Picasso to make nowadays. But the thing is, Picasso only has a little over 1,000 paintings, which for machine learning is not enough. It's not nearly enough. So the plan B is filtering by genre, and I thought about, yeah, I'll just get the most generic kind of painting I can get, because then I'll get a lot of it. So I just got little over 20,000 images of landscapes, because, well, people like to paint landscapes, and there is a lot of it available on the internet. And because the thing about machine learning and about image-based algorithms in machine learning is that you have to have over at least 10,000 things, otherwise the algorithm just gets confused, and it's not enough for it to know what exactly is that he has to reproduce. So yeah, I got all of these images, and the way that I did it, in case you're wondering, I didn't do it manually. I just coded this very simple scraper. It just crawled through the website and just downloaded all the images, and then I made a batch of it. And I put it all of them in this directory folder, which I called images. And the algorithm, the first part of this project has a phase of trying to format the images into shrinking them down to 64 pixels. Because the thing about this algorithm is that it doesn't really work with images above 256 pixels yet, because otherwise, for the algorithm, that's just considered noise. So yeah, I shrunk them down to 64 because my machine isn't so powerful, so I wanted to get them as lightweight as possible. So we had this pre-training part of the thing. You just put all of the images that you have, and you specify what's the final data file that you're going to want to call, which is going to be a zip file or anything. NPZ format is, it comes from the Python thing. It's good for this thing because it doesn't really compress all the images. We cannot have loss of the quality of their images at this point. Otherwise, it could compromise the success of the algorithm. And I specified the size. And then this part of the script just does everything for us. We just have to run this command. And the next thing that we really need to have is a really good processor. The thing about that, the processing power, which is, for me, I think it's the bottleneck of machine learning at this point. You probably have to install something like CUDA. It's by NVIDIA. It's available online. It's just something that is gonna sort of hack your processor into overclocking and just being more powerful than usual. It sort of unlocks all the GPU and GPL layers of the processor, which is this secret compartment in case you have to do something that's really heavy on your machine. And in case of my machine, I have 4 gigabytes of GPU. It's not great, but it's not but it's doable. The thing is that the only thing that changes is that if you have a not so good machine, it's fine. You're going to be able to run it. The thing it's going to take longer, and your machine may die in the process. But yeah, apart from that, it's going to be fine. And the last three things, I think they're definitely the most important things here, because whenever people ask me stuff or ask me advice about, hey, how do I get into machine learning? Well, the thing is that you have to be prepared for like not understanding stuff for quite a while, for being confused, for not being where to start to like fix your algorithm, to wait for the algorithm to run, which can take quite a while, and like persist over whatever it is that you think it's not working and you're not understanding why. That's definitely the most important thing when learning these things. And the training part, which is probably the most fun one. So what you have to do here is just take the data file that you got that has like the 64 pixels image that you just formatted. You have to specify like a folder for the output. And the way it works, like the code for each of those steps, and you don't really have to understand it because in this case it's in Python. I still wasn't able to reproduce it with TensorFlow.js, but we're getting there. The way that it works, and the part that you just need to pay attention, is that you have the ReLU, which is it's something that helps you classify things and helps you generate new artwork. And basically, the way that algorithm works in this case is that you have a couple of layers. Layers inside a convolutional neural network is like a stage. It's like several filters that you need to run your image by. And the ReLU is something that's gonna like get data from this layer to the other layer to the other layer to the other layer. And all of these layers have like a thing that they think it's more important. For example, the first layer of convolutional neural network is going to take care of the colors richness. The second layer is going to take care of the depth of the stroke, if you may. But each of them is going to try to reproduce a certain part of the style, and the ReLU is the thing that's going to take that information onwards. And what is important here to understand is that when we see the code for the discriminator, it's basically exactly the same thing, but different order. So I think it's really interesting because it's literally the same algorithm, but reversed. And again, you don't need to code this. This is already ready by several of the frameworks out there, like TensorFlow, like Keras, like Chainer. But it's nice if you want to understand how things work to just take a look at the source code and just like taking a chance at it. I really like doing that as well for client-side code. Like I usually, when I have a problem that I cannot solve, like in React, for instance, it really helps if I get the source code in Node modules and like realize how that works. Sometimes that helps. And the way we're going to run this is we're going to run this framework called Chainer. It already has implementation for the DC GAN, which is that full name that I described a couple of times. We're going to ask it to generate the trained model for us. And the whole training basically took 16 hours for me in this case with this machine. And in the beginning, you just see blurs of color, and they keep changing. And it's really cool because you can see like what's the computer seeing at several stages of the algorithm, but eventually you start seeing them like narrowing down and becoming more legible for us humans. And at this point, you have to stop to make some adjustments. Like if you see that, well, the algorithm is running for quite a while and I still cannot see anything that resembles whatever it is that I expect it to be seen. So you have to stop, make some adjustments to those layer things that I was talking about. And after you get the satisfying result, what we do here is get whatever the chainer has spitted out for us, we convert it to Keras, which is another library in Python that is really cool for machine learning. And the thing about Keras is that it's compatible to TensorFlow.js, which is what we're going to use to run this in the browser. And you just have to pay attention to that part. It's fine. So basically, we're going to have this conversion thing, getting the like chaining things, getting from the chainer to Keras to TensorFlow. And the part that we are very interested in at this point is the TensorFlow part. And for TensorFlow, it just spit out like a JSON file of a lot of things that like we don't know what it is, but the computer can interpret it in the right way. So we're going to use this very simple object declaration. So basically, the only thing we need to set is a path to the trained model, and the rest of the TensorFlow architecture is going to do the magic for us. It just interprets and spits out the result. I have this other options here set out, like I need to let the algorithm know what's the image size, otherwise it's going to misconfigure stuff. The latency is just something that you use for when you're transitioning from one image to the other. It's like something that tells it, like, hey, please don't go so fast, otherwise I'm not going to understand what's going on. And animate frame is something that I'm using for the CSS. And the thing is that you get something like this, in my case. That's one of the generated artworks, and you're able to run that on the browser, like the whole machine learning part is running on the browser, which is very interesting. The thing that I like the most about TensorFlow.js, and a lot of people ask me that, okay, like, JavaScript isn't really a language for like heavy calculations. Yeah, we all know that. But the thing is that we're all here, we're all like 900 people in this conference because we know JavaScript. And JavaScript is the language that most people know on Earth. So having stuff like machine learning also being able to run in JavaScript, for me, represents like this revolution into whatever it is that we think we can learn. Like, it's a lot easier for us to try and learn machine learning if we don't have the like learning curve of also having to learn another language. So I think like there's a very big importance of democracy of access here. Because previously, machine learning was this thing that was considered, well, that's for research folks, and like that's very academic, or I have no idea what's going on because this paper is super hard to read. And it's usually the case, and I'm really glad that we have this technology that's able to run in a language that's like more familiar to all of us, because it means that now there are no barriers for learning this, basically. And another thing that's very interesting about running machine learning in JS is that, as you know, like the browser can run things dynamically. And previously, the way that we did machine learning in the browser was like, obviously, like send a request to the backend is going to process that and give you back a response. And that takes a while. So if you're able to do all the calculations and the stuff for the machine learning part in the browser as well, you're going to get like a lot faster results. You're going to get even dynamic results if you have to. Like if you're having like a simulation, if you have like events in the client side layer, and you want to respond to that immediately using machine learning, now you can, because you don't have to send like an HTTP request and wait for the response. So that's really cool. So conclusions. These are the images that I was able to generate. They're all images of landscapes, and as you can see, they're pretty abstract because you have like a very intertwining characteristics of all the styles of landscapes, because like they came from different styles. Like a couple of them were very realistic, a couple of the other ones were very like abstract. But I have to know that I really was proud of the result, because like if I saw this in any museum, I would think that, well, whoever did this was a human, because that's usually not even something that you think at museums. But what is interesting here as well is that I was able to see like a lot of the elements in the arts, in the artworks that I fed. For example, you can see a lot of the colors that came from the training phase. You can see a lot of the stroke styles. You can even see like a couple of elements. Like in a few of them, you can see that there's mountains and stuff. You probably cannot see it right now because it's tiny. But yeah, I think like the results were really good. And I got 84 samples from 64 by 64 generated from this thing. And I noticed that there was a high variance of quality in each generated work, because like there was some artworks that were very like similar to the ones that I fed. And that was almost like bizarre to realize how this algorithm could reproduce in such richness of details. Some other one was like out of the box, like I don't even know where it came from. And one of the reasons for that is that this algorithm, and as well as like most of the other image-based algorithms for machine learning, are still very attached into thinking like what is real and what is right and what is wrong, rather than like actually assimilating and learning brush patterns or other things or learning styles. But that's a personal guess. The other things is that like some styles are very hard to reproduce rather than others. For example, before I ran this with landscapes, I ran this with artwork based on mythology. And shit, mythology is hard because like you can get paintings based on Greek mythology, you can get paintings based on Nordic mythology. And they're all very different. So like the most different things you get, the less you can actually like assess if it actually corresponds to whatever I trained or if it's just a crazy mix. I think a very interesting experiment here could be to just feed images that are more similar to each other. Like if I was doing some experiments on like still nature, that would probably, or like paintings of flowers, so that could probably be more accurate in the sense that we could probably see a lot more details from the things that we fed. Because if they don't change that much, it's easier for the machine to understand what are the important elements in each image. And for creative computers, I really hear a lot of people saying like, yeah, machines are really good at calculating and like doing this manual stuff that can be like reproduced, but they'll never do creative work. They'll never write a poetry. They're never gonna do stuff that us humans are capable of doing. And I think nowadays we're reaching a point, we're not quite there yet, but we're reaching a point where machines can also do creative stuff based, of course, on like previous human contributions and stuff. But we already see machines doing machine learning based songs. We already see machine learning doing artwork. For example, there's this short film, it's called Sunspring. You may recognize this guy from Silicon Valley. And the like script for the lines for this film was completely generated by machine learning. Which is very interesting because like obviously there's a bunch of parts where like whatever the characters are saying don't make perfect sense. But you can actually understand the story play and you can understand like some feelings that the characters are feeling, and that was all generated by machines. There's also this poetry, it's probably tiny, so you don't need to read it right now, but there was this, Google trained this AI to generate poetry based on previous samples from Bukowski, from Ernest Hemingway, and it was able to generate this poetry that if I was reading myself for the first time, I would think it came from some angsty teenager, like musing about life. And that is very scary because the thing is that there's context there and the lines make sense. And we can actually generate that by machines as well. And this other thing, and it's unfortunate because I think Sony removed this video from YouTube, but I'll try it in a sec. But Sony trained an AI to write a song inspired on the Beatles, like the instrumentals part, and shit, it's very accurate. And like it's very, like if I was reading that, if I was listening to it, I would think like, yeah, this band obviously really liked the Beatles. Because like you're able to feed all of these patterns and all of these like parts for the guitar, and the machine is already able to reproduce that in a way that it's not some crazy noise. So that's actually pretty cool. And in all of these examples, we can see that there's always like the training phase, but at the same time, since machine learning is actually like a black box, we don't really understand why the machine learning algorithms are doing or spitting out the result that they are. We just take a look at them and hopefully try to change the weights in the layers, as I said before. But we don't really know why they are spitting that result, and we never will. It's just like, at this point, the thing with machine learning is that it's very trial and error for us humans. So like not knowing why they are spitting out those results, I think I at least interpret that as some sort of like creative unpredictability. Because it's the same thing as humans. Like we see a lot of paintings from a lot of different authors, and like our head just interprets that and it mixes, and we are able to like do some creation ourselves, but we don't really know why we're doing like this thing in red the way that we're doing. We just do. And I think in that point, we're very similar to the way that the machine works at this point. So going back to Kosuth, he didn't make any of this. But the thing is that all of this means a chair. And that's right there for me. For me, art is making meaning. And I was able to make meaning out of paintings that I did using my computer. I didn't make all the paintings, I didn't do anything, but that for me means something, as well as the chairs means a chair to most things, to most people that are looking at it. So that's art for me. And what's art for you? I'd really like to hear that. If you have some time, catch up with me later on. This experiment and some other ones about machine learning are there on my repo on GitHub. There's some other ones that you can see that are like literally 100% in JavaScript, and some other ones that are Python-based. There are some other ones that are mixed. And if you have any questions or feedbacks or whatever, catch me up on Twitter. I'm there. That's it. Спасибо.
Спасибо. Any questions? Oh, okay, I'll try to keep order.
Hi.
Hi.
Thank you for your report. I have just one question. What's the main difference between the human and the machine, in your opinion?
My opinion is that at this point, the machine is still very reliant on having references. We still have to conduct the training in a very supervised way. So that means that for the machine to come up with these things, we have to feed previously created stuff by humans. And another thing that's very important at this point is that machines don't have conscience. Which is the whole thing that we talk about singularity and stuff, which is, it's going to be scary if it happens, there may happen, but the thing is that if the machine doesn't really have any conscience, that we don't really have the interference of feelings, for example. Picasso had the blue phase, which was a phase where he was sad, and that directly reflected into his work. And we're never going to have that with the machine at this point. But yeah, I think that's that. But at the same time, we can see very specific applications of creative work by machines. There's this rumor, I'm not sure if it's true, but I don't doubt it, is that Spotify and other sound streaming things are training AIs to come up with instrumental songs. Why is that? Because no one likes to pay royalties to humans, do they? So if those guys are able to create creative work that other people are going to consume, and it's going to be cost-free, then it's already an application of that sort of work with machine learning. So if you ask me, I think in 20 years we're going to see a lot of development on top of these things, but I'm not sure exactly what's going to be the next applications. I guess we'll see a lot more of that in the future.
Okay, thank you.
Thank you for your talk. Hi. You've mentioned this unpredictability in the results of machine learning, and my concern is that unpredictability still has to be stored somewhere in the database, and I would wonder if you know how actually does it look like in the database, or how much space does it take to store all that?
Yeah, that's a good question. Actually, the thing about unpredictability is that the way the machine interprets things is always going to be through code. As I said, the thing that we feed to the generator algorithm is going to be a matrix of a vector of 500 numbers. That for us doesn't say anything. I can't even turn that into an image. But apparently the machine does. And the way that it's unpredictable is because We don't know why. Why is it taking like all these 500 numbers and rendering this thing specifically? Now, that's what we don't know. And the interesting thing in machine learning is that you don't really need to store these kind of data after the training is done, because like, what are you gonna do with it? You already have your samples. So usually what I do is like I store these temporary data somewhere in the cloud. Google has a lot of services for cloud hosting stuff. They're not that expensive, but if you're having like a production thing with that sort of thing, you probably need to have some big data thing or somewhere to store that like huge chunk of data. And the unpredictable part for me is that like I don't really know why the machine spit out that like those samples specifically, and that's the interesting thing. The thing is that that's some inherent of what machine learning actually is, that we'll never know why the machine is doing that, not in like the close future. There's no way that we can interpret why it takes 500 numbers, turns that into machine code, turns that into zeros and ones, and spits out that. So like that's the unpredictable part.
Just trying to keep the first.
So the thing that is running in the browser, how much, it's similar to the previous question, how much code is that? How many, what's your bundle size for that?
Good question. It's not very big. The thing about the most demanding part of that, it's just like the browser part is just one file, which is the TensorFlow.js part. It's just like the functions that we have in that file, and later on I can totally provide the repo in Twitter, is that like you have the functions that already abstractions that TensorFlow gives us on top of the like natural code. And it's like the functions are, okay, convert this and get the model, interpret that, and like generate things. So the code for this is not very, it's not very hard to understand or anything. It's not even big. The bundle size is very small. The thing is that it is very demanding on the GPU. So when you run this on a browser, and that's the reason why I didn't show it on the browser, is because it takes a while for you to change from one image to the other, for example, because it has to generate and do all the calculations for interpreting the model into what's going to be an image. So like, that takes a while because it's very heavy on the GPU.
Is it, if you give it the same numbers, does it spit out the same image every time? Is it
no,
deterministic
I tried
like that?
that.
Okay.
I tried that. No, which is very interesting. I don't know why. But no, it doesn't. It's because of when you run the algorithm and you feed the numbers, it's not like a specific reference to a memory slot like we're used to doing. It's like a reference of what are the principles that you have to apply to all these samples. Like what is the like color weight that you have to put? What is the brush size that you have to put? Those are just like parameters. Those are not like the actual results. So that was very interesting. It's a very good question.
Thanks.
Hello.
Hello. What will do people when machines will do creative work?
Oh, we're just gonna go to the beach, you know, relax. I mean, in my case, I live in Rio. No, the thing is that, like,
What do you think about?
Yeah, that has a lot of very interesting implications. One thing that I really like talking about is like the universal basic income, because soon, and not even because of the creative work, like there's not going to be enough jobs for us to do as human beings. So that's probably going to lead a lot of people not having like necessarily professional occupations, and that's fine. But the thing is, like, the machines are going to be able to do that, the creative work, all they want. But the thing is that you're still a human, and you'll also be able to do that as well. Maybe you'll have like some robotic competition, but like I even think that I could produce something that is artistic based on those samples generated by the computer. So I think it's an iterative process. It's not like, okay, they're replacing us, shit. It's just like, yeah, we're going to be able to do that as well as them, and maybe that's even an input, a creative input for us humans. But that's just my personal opinion.
Thanks, lecture. I have a question about learning stage. I I didn't catch during this stage if that images are split into parts. For example, face is split a shape of face, shape and color of lips, eyes, and so on. Or maybe this machine is working with just colored spots.
Yeah, that's a good question. The thing is that, like, according to different kinds of images for faces, for example, since we already have so much work on facial recognitions, we have like very specific ways to draw faces. We have these things called landmarks, for example. The landmarks are going to be points in your face where like the machine is able to calculate the distance between like both your eyes, for example. So you're going to just draw these points like here, 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 like mapping your face. And therefore, if you're running this algorithm with a facial aspect, it's probably going to be closer and more attached to an actual image of a face. It's not going to be as sandboxed as doing landscapes, because we already have so many things that are like good parameters for describing faces. And the thing about that is that like it's a very wild mixture of color references and brush sizes and like size of images, and so like therefore you have a lot more variance. But as you can see on the face examples, you really can see like, yeah, it's a face, like it's not a face of someone that exists, but it's much more close to an actual face because you have all these other parameters like the landmarks, like embeddings. Embeddings are something that in machine learning we use to sort of like have measurements of the faces. Because like for facial recognition and machine learning, you don't really use like references of color, because like what if you change the color matrix in the image? It's my face gonna stop being my face? No. You need like this small metrics of what's the size of your nose, what's the size of your eyes, what's the difference between like your eyebrows and your forehead. And the machine does that automatically as well. Like it gets those embeddings and it's able to transform into like something that's more accurate because it's more number based. But yeah, did I answer your question? Sorry.
In general,
I got lost
yes.
in my answer.
Thanks.
Thank you.
Hi, thank you for your talk. I didn't quite understand, was that TensorFlow is an abstraction over some Python library and it calls it internally, or it's just a JavaScript alternative to some Python?
Good. Yeah, TensorFlow.js is actually sort of an abstraction of TensorFlow, the original one, which is in Python. But in this case, you can always like do machine learning stuff out of the box with TensorFlow.js. The thing is that in this case in particular, they didn't really have a very good abstraction for this particular algorithm that I was running. So my answer to this was doing the stuff in Python and just transforming into TensorFlow. But you can like, there's definitely other abstractions or another, like if I wanted to code that like single-handedly in TensorFlow.js, I would be able to, I just didn't want to. But the thing is that there's a lot of other good abstractions for other kinds of algorithms, like a regular convolutional neural network, which is the one that we use to figure out if an image of a dog is an image of a dog. That already exists in TensorFlow.js. There's a bunch of other very interesting examples in the repo for TensorFlow.js. There's one where they like respond to stimuli on the webcam. Like if you turn an object, the algorithm is gonna know like what direction are you turning to. Anyway, like there's all these other stuff that you're able to make on TensorFlow.js out of the box. You don't really have to do anything in Python. That's just like in case that you need to or you want to.
Hello.
Hello.
Thank you for your talk. I want to ask, what if we can take pictures from some animation that represents some real real town, for example. It will be, well, quite huge amount of pictures probably. And then make a computer to compare the real town and these pictures, and ask it to make some algorithm to make
A fantasy city.
well, yeah, some kind of representation of real towns in this artist style.
Yeah. Good question. Do you know that's already being made? Do you know by who? Google. They have access to a lot of images of cities, and that's very interesting because like how we see machine learning nowadays, like whoever's gonna win the battle of who gets the best algorithm is the guys that have the most data to train stuff, and Google has a lot of it, obviously. So like they already are making very interesting experiments with that. Like I've seen a couple of fictional cities that they were able to make based on actual cities, and I've already seen like a bunch of their studies regarding image completion, which is something that like if you're taking a picture and I put this bottle in front of my face and I remove the bottle out of by picture manipulating, algorithms are able to complete the missing part of the picture. So like Google's already making a lot of very interesting progress with that. They're one of the biggest guys in like doing machine learning stuff, obviously, because they have access to so much data. Especially user data is also very important. It's concerning because like they're sort of like using a lot of data from us that they really shouldn't, and there's like privacy infractions to that, but that's basically what they use to sort of like refine the ad market experience, for example. They know what to offer you in terms of products, in terms of whatever, because they're able to track so much of what we do online. And having all those raw data, this chunk of data, is very good for machine learning because like when you have a base of billions of users, then you have like input for a lot of different stuff and for a lot of experimenting, so.